Hello, my name is Cuc Dinh. I also go by Cookie, and I'm currently working as a postbac with Dr. Mark Morris and Dr. Anna Turlo at UCLA. Together, we are working on making high-resolution dust color temperature maps of the inner half-parsec of the Galactic Center, which is the center of the Milky Way. Now, what's in the Galactic Center? The most notable feature is the supermassive black hole known as Sagittarius A star. Surrounding this is a cluster of young massive stars. We're talking about beast stars, and these are also isotropic in distribution and counterclockwise stars. Beyond this, there are also compact dusty objects, such as G objects, as mentioned by Dr. Anna Turlo a few days ago. This is an artistic rendition, the right image. It is a dusty object thought to be a product of binary mergers within the vicinity of Sagittarius A star. Beyond this, there are also extended features such as speeding pieces of gas like the bullet, the mini cavity, which is a low density bubble thought to have a U shape down here, as we see in the bottom left. The IRS-13 East complex, which part of it is thought to be intermediate mass black hole candidate, and a linear feature, which I will go into detail later. Now, one way to really look at this complex environment is to look at the temperature, because the temperature gives us an understanding of how the physics can work. For example, with the G objects, we know that it's dusty, so it has to be cold. As to how cold it is, we still don't know. So if we could figure that out, we could actually see like how the dust really interacts with this object. That being said, I use near and mid-infrared data to create a dust color temperature map and to look at hot and cold features, as well as just look at how extended objects we know already really work. Now, for the first data set, I'm using a near-infrared-ish. It's a bit longer than a typical near-infrared data set, but I'm using near-infrared data collected by the NearInfrared imager at the Keck Observatory. Its central wavelength is around 3.8 micrometers, and the most noticeable aspect about this data set is that the point sources really come out in here. So these are all stars, by the way. Now, the mid-infrared dataset was collected in collaboration with Dr. Reinhold Scholder. The biggest difference between this and the LP dataset is that you see the dusty structures more. So this arm right here is known as the northern arm, and it comes from the mini spiral, which is spirals of or arms of ionized gas spiraling towards Sagittarius A star, which is the supermassive black hole here. The central wavelength here that we should know is 8.6 micrometers, and the pixel scale is actually a bit larger. So the resolution is not as high as the L prime data. Now, when we take the ratio of those fluxes and consider the Planck function, we can actually extrapolate the temperature using that function. And we end up getting a temperature map seen here. Now, I put the mid-infrared data set for reference, but if we see here, the northern arm that comes down here actually shows up as colder. This is around 180 to 215 Kelvin, whereas the mini cavity up here is also a bit warmer by like 20 Kelvin. The hottest region up here is around 350 Kelvin, and the ringing you see right here in the mid and the color temperature map is an artifact. Now, I'm going to go ahead and separate this presentation into two parts, the first part being hot and cold features, and the second part being extended features. One thing to note is that all of this data has not been published yet. This is still a work in progress. So yeah, the first part is the hot and cold features. Now, when we are looking for G objects, we want to find cold features. However, the question comes up with is that what is hot and what is cold? Because if you see it in the color temperature map, that means there is a discernible temperature difference. However, it doesn't necessarily mean that it's significant. For example, this object right here is known as IRS-1W. You can see it and it's obviously circular and somewhat compact, but comparing to its background temperature, it's not actually thermally significant. That being said, we look at the temperature map and we collected all compact looking objects by manipulating the scale. And then we considered the temperature of that feature itself and compared it to a background using a ring, so an inner and outer analysis. We then plotted the distribution of the temperatures down here, and seeing how the distribution went, we decided to put a threshold temperature difference of 10 Kelvin. So whichever had a source that was 10 Kelvin higher or 10 Kelvin lower than its background was considered a hot or cold feature. This led to us having 36 candidates in total, and of these 36 candidates, 13 are unknown, mostly around this area right here. Now, if you were to go back and compare with the known G objects right now, aside from ID14, I also plotted not only the G objects, but also infrared excess sources from Eckhart et al. 2013 and Zatarsky et al. 2016, because these could also be candidate G objects. But aside from ID14 right here, ID38, 48, and 54 do not correspond to any of the G objects known. So this might be new G objects. Now, for the next part of this presentation, I'm going to go ahead and shift the focus to extended features, starting with the Epsilon source right here. Now, The Epsilon source, first discovered by Yusuf Zada in 1990 in the radio, seen right here beside Sagittarius A star, which is that giant dark blot, is incredibly complex in the sense that it has a considerable internal velocity structure followed by, it just being incredibly tumultuous due to its proximity to Sagittarius A star. It retains this apostrophe-like shape right here. And, there should be, we are continuing to investigate it right now. The next feature you want to look at is the bullet. So this bullet, if you remember correctly, there was this large source that had a lot of ringing behind it. This bullet is below that source. It's called the bullet because it looks like a speeding bullet, but also because it is moving incredibly fast in the direction that we expect. So it's going this way. And now if you were to break down the bullet from its head to tail structure, we actually see that the head is 50 Kelvin, around 50 Kelvin colder than its background. This is one of the coldest features we have in our hot and cold candidates. We also see that the temperature increases as we go down the tail. Now, the next component we are going to go ahead and look at is the mini cavity. As mentioned before, the mini cavity is a low density bubble, and this isn't, it's cut off in this image because of the L prime data set, but this is actually the western edge of the mini cavity. We actually see that it increases in size at the end, so it takes on a more fatter shape, looking more like a crescent in the color temperature map. Now, moving on from the western mini cavity, we also see the IRS-13 East complex, which is here. It's not part of the mini cavity. It seems superimposed, but we don't know for sure if it is inside the mini cavity itself. Now, the IRS-13 East complex is not just made out of stars. IRS-13 East E3 right here is actually still up to debate as to what it is. The reason for this is that E4 and E2 are Wolf-Rayet stars. And so some have speculated that E3 is actually the product of a shock between the colliding winds of these Wolf-Rayet stars. However, if you were to look at the X-ray sources or X-ray data sets, we actually see that E3 is incredibly strong in that regime. So some other people have also considered it or argued that it could be an intermediate mass black hole, and that's still up to debate. But if you were to look at the color temperature map itself, we actually see that E3 is a cold core right here. This is, and surrounded by this cold core is a warm shell. This shell is around 15 Kelvin hotter than the core itself. As to what's causing that, we're not sure. And that's still up to investigation. Now, sorry?
2 minutes.
Okay. Now, the last feature we're going to go ahead and look at is a linear feature. This bisects the northern arm. And we can see this in the L prime data, the mid-infrared data, and also the color temperature map. However, the thing with the color temperature map is that we actually see two strands. As to whether or not this strand actually exists, that's still up to debate. It could just be us trying to look for another pattern. We don't know. However, because it goes through the northern arm as seen right here in the M band, there is a possibility that it's part of the northern arm. However, unlike the northern arm, it doesn't show up in the radio, and there's a possibility that it doesn't also show up in bracket gamma. So this suggests that it could be purely dust. It could also be synchrotron radiation, but as mentioned before, it doesn't really show up in the radio, which synchrotron radiation typically shows up in. So we also have to figure that out. The next step of this project is to incorporate extinction. As mentioned before, we're using near and mid-infrared data. We could use the power law described in Fritz et al. 2011 right here because it kind of, the near-infrared data set kind of goes between that regime. But if you were to look at the mid-infrared right here, it doesn't really follow a power law, and we still need to figure out how the extinction is working there. And as to why we need to account for extinction, well, extinction goes along the line of sight, but locally speaking, it also varies in order of magnitude. So some of the candidates that we are seeing could possibly be attributed to extinction clumps within that region. So we just have to discern whether or not those are actually clumps and candidates that we should take into account, or if it's just extinction really playing with that. And I will leave this summary up and take questions now. Thank you.
Thank you very much. Any questions? Oh, it's Ryan. You can.
Thanks for the interesting talk, Cookie. I had a question about IRS-13E, these two potential Wolf-Rayet stars. So is the claim that that bright source is that you're resolving the shock between the two winds, or that there's an unresolved pair of Wolf-Rayet stars there, and the bright source is the shock?
So the claim is that, okay, E4 and E2 are known to be Wolf-Rayet stars, but we don't know what E3 is. And some people have claimed that it's the shock between the winds of E4 and E2 because E4 and E2 are Wolf-Rayet stars.
What's the separation distance between E2 and E4?
I would not know, but for reference, this is around 0.4 arc seconds. So yeah, sorry, I would not know. I would have to.
Okay.
Yeah.
Okay. Yeah, I'm just wondering if those, since the stars are resolved, they're probably pretty well separated, especially towards the galactic center. And so I'm wondering if it would have enough, if the winds from those two stars that are separated that far away would, yeah, be strong enough to power that Bredman emission at L band. But yeah, that's interesting. I wasn't aware of this.
Okay. There's one question in the Slack from Thomas. Is the assumption that all emission is optically thin, or are you correct?
Sorry.
The assumption is the all emission is optically thin, or did you correct?
I believe that is assumption.
Okay.